Welcome. It's now time to enter into integral calculus of several real variables. Today we are going to start our fourth chapter, line integrals. Right now we shall start our first module of this chapter, Introduction to Integration. In this module and onwards, we shall study integral calculus of several real variables. Our main aim is to introduce and then study the concepts of first line integral and then multiple integral. In fourth chapter, we shall devote ourselves to the study of line integral, and in the next we shall start multiple integral. In this particular module, first of all we shall recall the notions of integrability as were introduced by Newton, followed by Darboux and Riemann. We shall also mention the first and second fundamental theorems of calculus which we need for our future discussion. In short, in this module, we shall prepare the framework we need for the following modules. First of all, let us recall the notion of Newton integration. The notion is quite simple. The process of differentiation shows how the functions change into different ones, and Newton integration takes care to retrieve the original function back. That is, we can consider integration as an attempt to undo the process of differentiation. So, to a given function, we will try to find another function whose derivative is the given function. The second one is called as an antiderivative of the first one. That is, Newton integration is the process of finding antiderivative. We start with defining antiderivative of a real valued function defined on a subset of the real line. Let I be an interval and f be a real valued function defined on I. A function f from I to R is said to be antiderivative of f if the function capital F satisfies the following properties. First, the function capital F is continuous on the interval I. Secondly, for every x in the interior of the interval I, capital F dash x should be equal to small f x. That is, in the interior of the interval I, the derivative of capital F and small f coincide. If such an antiderivative of small f exists on I, then small f is said to be Newton integrable on I. The above definition is formulated in this way because we like to set the notion of antiderivative in two settings. In order to have a derivative at a certain point x, a function must be defined on a neighborhood of this point x. Therefore, the most natural situation is when we search for an antiderivative of f in an open interval a b containing x. Every point in such an interval has a neighborhood within the interval so that an antiderivative capital F can be differentiated everywhere satisfying the condition for all x in interior of AB, which is nothing but the same interval, capital F dash x equals to fx. Again, since differentiability implies continuity, such a function f is automatically continuous on open interval AB, which is nothing but the interior of it. However, we often desire for an antiderivative capital F of small f on a closed interval AB. We are considering a bounded closed interval. Then the definition specifies how to extend the above natural situation as explained. We still want that for every x in the open interval AB, capital F dash x equals with fx. We note that interior of bounded closed interval AB is the open interval AB, because we cannot have derivatives at the endpoints A and B. So, to describe the desired behavior of capital F at the endpoints A and B, we use the second condition that capital F is continuous on bounded closed interval AB. Now, due to differentiability, capital F will be continuous on open interval AB. Therefore, the continuity condition basically just adds the requirement of one-sided continuity at the endpoints of our assumed bounded closed interval, that is, right continuity at A and left continuity at B. We cite an example. We define a function f defined on the bounded closed interval say 0 to 5 by fx identically 9 for every x. Now we define a function capital F defined over the same interval and real valued by capital Fx equals 9x plus 1 for every x. Then evidently the function capital F is continuous everywhere on its domain, that is on the bounded closed interval 0, 5, and for every point x in the corresponding open interval, that is 0 to 5, we have capital F dash x, that is the derivative of 9x plus 1, which equals 9. Therefore, the function capital F is an antiderivative of the function small f on the given closed interval. Analogously, we can check that another function g defined over the same bounded closed interval 0 to 5 defined by gx equals 9x minus 1 for every possible x is also an antiderivative of the function f on the given closed interval. As a matter of fact, these two functions are antiderivatives of the same function small f on the given closed interval. The above example stipulates some interesting fact. Firstly, how did we obtain these antiderivatives? We guessed this applying our experiences with derivatives. Secondly, we can have more than one antiderivative to the same given function. This is why we always told an antiderivative. In fact, based on our experiences for any real constant c, the function capital Fx defined by 9x plus c is an antiderivative of the given function small f such that for every x fx equal to 9 on any given interval. Now, the natural question that may come in one's mind is, are there also any other kinds of antiderivatives of the function fx equal to 9 on any given interval? However, the answer is negative. The following theorem will ensure us that adding a constant to an already known antiderivative is the only way to obtain other antiderivatives. Theorem. Let capital F from I to R be an antiderivative of a function small f. It is also real valued and defined over the same set I. Here I is an interval. First, for any real constant small c, the function capital G defined over I given by gx equals capital Fx plus c for every x in I is an antiderivative of small f on I. Secondly, if capital H defined over the same interval I is another antiderivative of small f on I, then there exists a real constant c such that hx equal to fx plus c for every x in I. In the first case, we start with a constant and then find another function, that is another antiderivative. And in the second, we assume the existence of another antiderivative and then show the existence of a constant. Newton integral. Let capital F from I to R be an antiderivative of a function f defined over the same interval I. The Newton integral of small f is denoted and defined by integral fx dx equals to fx plus c for every x in I and for some real constant c. The above definition of Newton integral is called indefinite Newton integral. Definite Newton integral. Let capital F defined over a bounded closed interval AB, real valued, be an antiderivative of a function small f defined over the same bounded closed interval AB. That is, capital F satisfies the following properties. First, capital F is continuous on bounded closed interval AB, and secondly, the derivative of capital F is small f for every x from the corresponding open interval. Then the definite Newton integral of small f is denoted and defined by integral a to b small fx dx equals to difference of the values of capital F at b and a, that is capital FB minus capital F A. Now we are going to discuss the first and second fundamental theorems of calculus. Let A be an open set in R and f is a real valued function defined on A. We recall that a function capital F is called a primitive or an antiderivative of small f in an open interval I contained in the set A if and only if the functions capital F dash and small f agree on I. The first fundamental theorem of calculus tells us how to construct a primitive capital F from a given function small f, obviously at a point where the function small f is continuous, and the second fundamental theorem of calculus shows how to find all primitives from a given function starting from a particular primitive, provided the function small f is continuous. Let capital F be a real valued function defined over a bounded closed interval AB. Then for every C from open interval AB, small f is integrable over both the subintervals closed AC and closed CB. We define a function capital F over the bounded closed interval AB by capital Fx equals integral from C to x fu du. Let small x be an arbitrary point in the open interval AB. We keep it fixed. Then capital F at the point x plus h minus capital F evaluated at x equals integral C to x plus h fu du minus integral C to x fu du. So, this equals with integral of f with lower limit x and upper limit x plus h. Now, let us replace fu by fx plus fu minus fx in the above integral. We find the following: capital F x plus h minus capital Fx equals integral x to x plus h fx du. We observe here that integrand fx is independent of u plus integral x to x plus h fu minus fx du. So, the first one is nothing but h times fx. From this we have capital F of x plus h minus capital Fx divided by h equals with small fx plus 1 upon h integral x to x plus h fu minus fx du. Now, if the function small f is continuous at the point x, we can show that 1 by h integral x to x plus h fu minus fx du tends to 0 as h tends to 0. Thus, considering the condition of continuity of the function small f at x, letting h tend to 0, from the above relation we find that capital F dash x equals to small f x. Thus, we have the following theorem. First fundamental theorem of calculus. Let small f from bounded closed interval AB to R be such that it is integrable on every closed interval Ax, where x is a point arbitrarily chosen from the bounded closed interval AB. Also, let C from the bounded closed interval AB be arbitrarily chosen. Now, if for all x in bounded closed interval AB, capital Fx is defined by integral C to x fu du, then at every point x from the open interval AB where f is continuous, capital F is differentiable. Moreover, for every such x from open interval AB, capital F dash x equals fx. Next, we assume that the function small f is continuous over the open interval AB. We define a function capital F over bounded closed interval AB to R by capital Fx equals integral c to x fu du, where c is an arbitrary point in bounded closed interval AB. Then capital F is a primitive of small f. Now, let capital P be any primitive of small f. Since any two primitives can only differ by a constant, there exists a real number alpha fixed such that for every x in bounded closed interval AB, we can express capital Px equal to capital Fx plus alpha. We put x equal to c in the above and hence find Pc equal to alpha, because Fc equal to integral c to c fu du, which is nothing but 0. So, for every x from bounded closed interval AB, we find Px equals integral c to x fu du plus Pc. Hence, we have the following result. Second fundamental theorem of calculus. Let small f from bounded closed interval AB to R be continuous. Then for any primitive capital P of small f over bounded closed interval AB, we find capital Px equals integral c to x fu du plus Pc for every c and x from bounded closed interval AB. Now we shall study another version of this. Let small f from AB to R be continuous. Hence, it is integrable on every closed interval a to x, where x is an arbitrary point in bounded closed interval AB. Also, let C be a point arbitrarily chosen from the bounded closed interval AB. Then, for every x from bounded closed interval AB, we define capital Fx equals integral c to x fu du. Clearly, f is differentiable. Moreover, for every such x from open interval AB, capital F dash x equals to fx. So, we can write capital Fx equals to integral c to x f dash u du. We define another function capital G over the bounded closed interval AB by capital Gx equals integral a to x f dash u du for every x in bounded closed interval AB. Clearly, capital G is another primitive of small f like capital F. Therefore, capital G and capital F differ by a constant. Let capital Gx minus capital Fx equals to alpha for every x. If we put x equal to b, then we find Gb minus Fb equals to alpha. Now we put alpha x equal to a, so Ga minus Fa equal to alpha. That is, we find Gb minus Fb equals to minus Fa as Ga is 0. Thus, we have Fb minus Fa equals Gb, which equals to integral a to b f dash u du. So, we discussed about Newton integrals. We also discussed the first and second fundamental theorems of calculus. In the third module of this chapter, we shall study line integrals. Then we shall need these two fundamental theorems. Now we switch over to Darboux and Riemann integral. Now the question naturally arises, can the concept of integration be extended to a larger class of functions? That is, a class of functions containing the collection of all differentiable functions. Here we note that we consider functions defined on a bounded closed interval. One motivation is the following. If integral a to b fx dx exists in the sense of Newton, then it can be geometrically interpreted as the signed area of the region bounded by the x-axis the two vertical lines corresponding to x equal to a and x equal to b, and the graph of f joining the points AFA and BFB. Let us consider the function fx defined by modulus of x for every x in bounded closed interval -1 to 1. Here, we can easily find the signed area, but we know that the function is not differentiable at the origin. In the 19th century, the notion of integration was extended by Darboux and Riemann for functions defined over a bounded closed interval. An interesting point is that there exist functions integrable in these senses having at most denumerably many points of discontinuity. We briefly discuss it here. We start from the notion of partition. Let AB be a bounded closed interval. By a partition of AB, we mean a finite collection capital P of points x0, x1 continued up to xn. All these points are collected from the bounded closed interval AB, satisfying A equal to x0 less than x1, continuing less than xn minus 1 less than xn, which equals with B. We denote this partition by P equal to A equal to x0 less than x1 less than continuing less than xn minus 1 less than xn equal to B, or simply by P equal to A equal to x0 comma x1 comma continuing xn minus 1 comma xn equal to B. Norm of a partition. Norm of the above partition P is denoted by norm P and defined by norm P equals to supremum of the length of the subintervals, that is supremum of modulus xi minus 1 where I runs over from 1 to n. The collection of all possible partitions of AB is denoted by the symbol script P AB. Refinement of a partition. If P1 and P2 are two partitions of a bounded closed interval AB, where P1 is a proper subset of P2, then P2 is called a refinement of P1. One can easily check in such a case norm of P2 is either less than or equals to norm of P1. Now we discuss Darboux sums of a function with respect to a partition. Let small f be a real valued function defined and bounded over a bounded closed interval AB. We consider an arbitrary partition P equal to A equal to x0, x1 up to xn minus 1, xn equal to B of AB. Since f is bounded over AB, it is bounded over every non-empty subset of AB. So it is bounded over every such subintervals. We define for every r equal to from 1 to n, capital MR equal to supremum of fx, where x is from the rth subinterval, that is from xr minus 1 xr, and small mr as the infimum of fx, where x comes from bounded closed interval xr minus 1 to xr. The existence of such capital MRs and small mrs are assured by the completeness axiom. Moreover, for every r from 1 to n, small m less or equal to small mr less or equal to capital MR less or equal to capital M, where small m is the infimum of fx, where x runs over the domain of f, that is the bounded closed interval AB, and capital M is the supremum of fx, where x from bounded closed interval AB. We further define the upper and lower Darboux sums, which we denote by UFP and LFP of f, corresponding to this particular partition capital P by the following: UFP equal to capital M1 x1 minus x0. M1 is the supremum of f over this interval x0 to x1, and x1 minus x0 is the length of this subinterval, plus M2 into x2 minus x1. The sum continues up to the nth term mn times xn minus 1. So, summation r equal to 1 to n capital M are xr minus 1. The lower sum is defined in the similar fashion, only supremums of fx in the subintervals replaced by infimums. That is, LFP is summation r equal to 1 to n small m r xr minus 1. It is obvious that small m times b minus a less or equal to L times LFP less or equal to UFP less or equals to m times b minus a, where small m is the infimum of fx and capital M is the supremum of fx, where x runs over bounded closed interval a to b. We further note that if in particular small f is constant in a particular subinterval xi minus to xi of AB, then small m times xi minus 1 less or equal to small mi multiplied by xi minus 1 equals to capital Mi xi minus 1 less or equal to capital M xi minus 1. Here we considered in the ith subinterval f reduces to a constant, so its infimum would be equal to its supremum. Now let P2 be a refinement of the partition P1, then it is easy to check that small m into b minus a less or equal to LFP1 less or equal to LFP2 less or equal to UFP2 less or equal to UFP1 less or equal to capital M times b minus a. This means inserting more points in the partition increases the lower Darboux sum and decreases the upper Darboux sum. However, both the sums always remain bounded even in the above by capital M times b minus a and bounded in the below by small m times b minus a. Using completeness axiom, we can further say that the collection of all upper Darboux sums has a finite infimum and the collection of all lower Darboux sums has a finite supremum. Here the collection corresponds to all possible partitions of AB. Let us define under bar integral a to b f equal to supremum of LFPs, where P runs over arbitrary partitions of AB, and upper bar integral a to b f equals to infimum of UFP, where P is any partition of AB. These two real numbers, lower bar integral a to b f and upper bar integral a to b f, are unique. They are known as the lower Darboux integral of f over AB and the upper Darboux integral of f over AB. In case these two integrals are same, we say f is Darboux integrable over AB. The common value is called the integral of f over AB and it is denoted by integral a to b f or by integral a to b fx dx. The celebrated calculus book authored by Tom M. Apostol, volume 1, narrated the process of concept of Darboux integral in an elegant way. It used the notion of step functions. We give a little summary here. Let f from bounded closed interval AB to R be a bounded function. Now f is said to be a step function if and only if there exists a partition, say capital P of AB, such that the restriction of f over each subinterval reduces to a constant function. Let f from AB to R be a step function. Then there exists a partition P with the points of partition as a equal to x0, x1 up to xn minus 1 and xn is B, such that there exist constants C1, C2 up to Cn satisfying fx equal to Ci in the ith subinterval. We define S integral a to bf equal to summation from I equal to 1 to n Ci xi minus xi minus 1. Here we used the S symbol before the integral sign to emphasize that the such notion of integral is valid for step functions only. As the right hand side contains finitely many terms, the above integral is well defined. We have to take care of the following points. First one, this definition of integral is valid for step functions only. Secondly, the values of f at the points of partition, that is the values fx0, fx1, fxn, does not affect the definition. Third, changing the value of f at finitely many points does not affect this integral. Fourth, the value of integral does not change under any refinement of the partition. Fifth, this process of integration satisfies linearity property of the integrand. Now let f from AB to R be an arbitrary bounded function. If for every pair of step functions L and U from AB to R satisfying for every x in bounded closed interval AB, Lx less or equal to Fx less or equal to Ux, there exists a mu such that S integral a to b L less or equal to mu less or equal to S integral a to b U, then f is said to be Darboux integrable. Moreover, such a mu is unique whenever it exists. This real number mu is called the integral of f over AB, and it is denoted by integral a to b f or integral a to b fx dx. That is, here we consider every pair of step functions, one which is always below the given function, another which is always greater than the given function. One can easily verify that for any partition P of AB, UFP and LFP are examples of S integral a to b U and S integral a to b L, where U and L are step functions as described above. Moreover, lower integral a to b F equals with supremum of S integral a to b L, where L is any step function defined on AB below F, and upper integral a to b F equals with infimum of S integral a to b U, where U is any step function defined on AB above F. The approach of Riemann was a little bit different than that of Darboux. Let f from AB to R be a bounded function. We consider any partition P with points of partition a equal to x0, x1 up to xn, which is B. Let xi I be a point arbitrarily chosen from the bounded closed interval xi minus 1 xi. We construct the Riemann sum of f corresponding to this partition P as RFP equals with summation I equal to 1 to n f xi I xi minus 1. If the limit norm p tends to 0 plus RFP exists finitely, then we say that f is Riemann integrable over AB. The value of the limit is denoted by integral a to b f or integral a to b fx dx. The most interesting fact in this regard is that the notions of Darboux integrability and Riemann integrability are same. That is, if a function f defined and bounded over a bounded closed interval AB is Darboux integrable over AB, then it is also Riemann integrable over AB, and converse is also true. Moreover, the values of these two integrals are same. Now one can easily understand the comparison between Newton integrability and Riemann integrability from the following remarks. In the first remark, we cite an example. Let us consider two functions defined over the bounded closed interval 1 to 1. f1x is mod x. Now clearly f1 is not differentiable, and next we consider f2x, which is defined by x if x is rational and otherwise 0. We can clearly check that these are Riemann integrable but not Newton integrable. In case of Riemann integration, continuity is not a necessary condition for the existence of a primitive. We consider a function f from -1 to 1 defined by fx equal to x square sin 1 upon x for every non-zero x, and the value of f at 0 is 0. Then f is differentiable. Let its derivative be small f. Here small f is the primitive of capital F, but small f is unbounded and hence not Riemann integrable. Moreover, small f is not continuous at 0. So, in this module, we discussed the notions of Newton integrability, Darboux integrability, Riemann integrability. We also studied the first and second fundamental theorems of calculus. We shall use these concepts in the subsequent modules. We conclude here.